Welcome back to this module on exploiting DLP using SIMD instructions. In this lesson I will discuss different ways of supporting multiplication operations in SIMD instruction sets, since the result of a multiplication requires more bits than its input operands. Overflow, when we perform addition, overflow occurs, but we know how to deal with it. When we multiply two n-bit numbers, so adding an n-bit number to an n-bit number gives potentially an n plus 1 bit number, but using saturation arithmetic we know how to deal with it. When we multiply two n-bit numbers, the result is a 2n-bit number. So the result is larger than can be represented using the same data type. Again, the question is, how do we handle this? How do we deal with this? Several approaches have been proposed and several approaches have been implemented. Even-odd multiplication, multiply high-low, reduction, or to exploit a special result register that can store the results in a higher precision. I will now discuss these approaches in turn. The Motorola Ultivec extension supports multiplying the even or the odd elements of the source register. For example, here we have the parallel odd multiplication. These are element 0, so this is even. This is element 1, so this is odd. So these two elements are multiplied. Minus 5 times 70 equals minus 350, and this can be placed in a result that is twice as large as its operands. And similarly, this is element 3, so we can multiply these two and the result is twice as large as its source operand. The problem with even and odd multiplication is that it may require extra so-called shuffling operations or permutation operations to order the results in the result registers. Intel, in its MMX and SSE extension, as well as other processor vendors, support selecting the low or higher order parts of the results. For example, here I illustrate parallel multiplication of signed bytes. Signed bytes lie in the range minus 128 up to 127. And the parallel multiply low byte indicates that the least significant byte of the 16-bit result is selected. So here we multiply, for example, A0 with B0. This gives us a 16-bit result, but this result stores only the least significant byte of the multiplication. Right? This is kind of clipping. This is very similar to clipping. Only the lower order, the lower order part of the result is significant. Sometimes it's fixed point calculation. Sometimes the fixed point is in a higher byte, and then we select the higher byte. Another technique to deal with multiplication is to reduce. Multiplication in multimedia applications is often part of so-called multiply, add or MAD operation, which is a central core operation in almost any digital signal processing application. So multiplication and then reducing the results sums the neighboring products to produce fewer results. For example, here we multiply 0 with 10 and 70 with minus 5, but we don't need the products, we need the sum of all products. Therefore, we immediately sum these two partial products and store the result in our factor register, which in this case equals minus 350. The fourth option to deal with multiplication is to employ a result register that is wider than the elementary data size. For example, MIPS MDMX avoids multiplication, the width of the multiplication problem by introducing a so-called accumulator. And this accumulator is 128 bits wide. And this accumulator, as in traditional accumulator architectures, there was an implicit operand called the accumulator, which was the source as well as the destination register for many operations. Here, it acts as the source and destination register for many operations, including the multiplications. So the partial products are all accumulated, are all summed up in the accumulator. And finally, when the accumulator, then truncation, then rounding takes place, so we lose no intermediate precision if we have a reduction operation. This completes this lesson. To summarize, all modern processors support SIMD instructions, SIMD instruction set extensions, which are very similar to short factor operations. We can use an existing register file, the integer, the floating point register file, to implement the SIMD register file, but nowadays it's usually a separate register file. Arithmetic SIMD instructions such as add and subtract often support saturation arithmetic to prevent overflow, and multiplication is somewhat challenging because the product is wider than the multiplicand and the multiplicator, and we need a larger register to keep all the result bits, or we can select only some of the result bits. This completes this lesson. Thanks for watching. In the next lesson, I will discuss some special purpose SIMD instructions and converting between different packed data types. Stay tuned.